In July of 2022, humanity saw the early universe more clearly than ever before. The first images from the James Webb Space Telescope appeared on screens across the world. They were meant to be a confirmation, a validation, a deeper, sharper look at a cosmic story we believed we already understood. The images were breathtaking. Thousands of galaxies scattered across the darkness, their light arriving from more than 13 billion years in the past. This was the universe in its youth, the first structures emerging from cosmic darkness. Or so we thought. What we didn't expect was to find galaxies that should not exist, not in a philosophical sense, in a physical one. These were not small, chaotic clumps of stars struggling to take shape. They were large, organized. Some showed hints of spiral structure. Others contained dense, central regions surrounded by rotating disks. They looked settled, mature, familiar. And they were everywhere, not rare anomalies, not statistical flukes, but repeated, consistent features of the early universe. The light from these galaxies began its journey when the universe was only a few 100 million years old. 300 million, 400 million, 500 million, mere moments in cosmic time. And yet, these galaxies looked old. That is the problem. According to everything we know about cosmic evolution, galaxies take time to form. A great deal of time. Stars must ignite, live out their lives, and die. Their deaths must seed space with heavier elements. Those enriched clouds must collapse again, forming new generations of stars. Gravity must patiently pull matter into rotating structures, shaping disks and bulges over billions of years. This process is slow, but the galaxies Webb observed looked as though that entire story had already happened. It's as if you planted a seed yesterday and returned today to find a towering oak tree, complete with centuries of growth rings hidden in its trunk. The timeline doesn't work. The numbers refuse to cooperate. This is what astronomers mean when they say Webb has detected objects that appear older than the Big Bang, not older in absolute time. The universe is still 13.8 billion years old. The Big Bang still marks the beginning of everything we can observe. But these galaxies appear more evolved than should be physically possible, given how little time had passed since that beginning. Our understanding of cosmic history is built on decades of observation and theory. We know, or believed we knew, how long it takes for the first stars to ignite. We know how long those stars must live before producing heavy elements. We know how gravity assembles matter into galaxies. These processes require time, lots of it. Yet Webb has shown us galaxies with masses equivalent to tens of billions of suns. Galaxies containing multiple generations of stars. Galaxies that appear to host supermassive black holes already grown to remarkable size. All of this in a universe barely out of its cosmic infancy. The implications are unavoidable. If these observations are correct, and multiple independent teams now agree that they are, then something fundamental in our understanding is incomplete. Either galaxies can form far more rapidly than we ever imagined through mechanisms we do not yet understand, or the early universe behaved very differently than our models suggest. Possibly both. Naturally, skepticism came first. Perhaps the distances were wrong. Maybe these galaxies weren't as far away, not as ancient as they appeared. But the redshift measurements, which tell us how much the universe has expanded since the light was emitted, were confirmed using multiple methods and instruments. The distances held. Perhaps the galaxies only looked massive. Dust can obscure light. Gravitational lensing can magnify distant objects. Young stars can shine unusually bright. These possibilities were examined carefully. Some cases were explained, many were not. The pattern remained. The galaxies were real, they were distant, and they were too mature for their age. This kind of mystery is not a failure of observation. It is the opposite. It is what happens when our instruments finally become precise enough to expose the limits of our theories. For decades, our models of the early universe worked remarkably well. They predicted the cosmic microwave background. They explained how matter clumps on large scales. They described the slow, hierarchical growth of structure from simple beginnings. But they did not predict this. They could not have predicted this. And that means something is missing. Some process, some condition, some aspect of the early universe that our current picture does not capture. The galaxies are not going away. They are written into the data. They exist under real physical laws, laws that we now need to understand more deeply. To grasp why these observations are so unsettling, we must return to the story we thought we knew. We must trace the orthodox timeline of the universe's first billion years. The sequence of events every previous telescope seemed to confirm. Only then can we see exactly where that story begins to break. The story of galaxy formation begins in pure light. At the moment of the Big Bang, there were no atoms, no stars, no planets, no structure of any kind, just energy. Radiation so intense that matter couldn't hold together. Particles collided and annihilated and reformed in a cosmic furnace that filled all of space. For the first 380,000 years, the universe was opaque. Light couldn't travel freely because it kept scattering off charged particles. Photons would move a short distance and then bounce off an electron. Move again, bounce again. The cosmos was a fog of light and matter locked in constant interaction. Then came recombination. The universe had expanded enough, cooled enough, that electrons could finally settle into orbit around atomic nuclei. Hydrogen atoms formed, helium atoms formed. For the first time, light could travel unimpeded across space. The fog cleared. We see the afterglow of this moment today as the cosmic microwave background, the oldest light we can observe, a snapshot of the universe at 380,000 years old. But with light came darkness. Once the photons streamed away into the expanding void, the universe entered what cosmologists call the Dark Ages. No stars had formed yet, no galaxies, just vast clouds of hydrogen and helium drifting through the blackness, slowly pulling together under the influence of gravity. That gravity, we believe, was shaped by dark matter. This mysterious substance, which doesn't emit or absorb light, had been there all along. It couldn't interact with the radiation that filled the early universe, so it began clumping earlier than normal matter. By the time of recombination, dark matter had already created an invisible scaffolding. Regions of slightly higher density, gravitational wells where normal matter could collect. The hydrogen clouds fell into these wells. They compressed, they heated, and eventually, after about 100 million to 200 million years, they became dense enough and hot enough to ignite nuclear fusion. The first stars were born. These weren't stars like our sun. They were monsters. Population 3 stars, astronomers call them, made of nothing but hydrogen and helium because no earlier generation of stars had existed to create heavier elements. They burned blue and brilliant. Some may have been hundreds of times more massive than our sun. They lived fast and died young, exploding as supernovae after only a few million years. Those explosions seeded the cosmos with the first heavy elements: carbon, oxygen, iron, the building blocks of planets and eventually life. But more importantly for our story, those explosions stirred up the gas clouds and triggered new waves of star formation. The second generation of stars could form from slightly enriched material. They were smaller, longer-lived, more diverse. Meanwhile, the dark matter continued its patient work of gravitational assembly. Small clumps merged into larger ones. Stars bound together by gravity formed the first dwarf galaxies. These were tiny by modern standards, perhaps only a few million solar masses worth of stars, irregular lumps without clear structure. But they were the seeds. The orthodox model tells us this process took time, lots of time. The first dwarf galaxies probably appeared around 400 to 500 million years after the Big Bang. They would have been chaotic places, stars forming in bursts, supernova feedback blowing gas out into space. Small galaxies crashing into each other and merging. Over the next few billion years, through countless mergers and acquisitions, these dwarfs gradually assembled into larger structures. 10 dwarfs merged to form a small galaxy. 10 small galaxies merge to form a medium one. The process is hierarchical. Bottom up, small to large. This is the foundation of modern cosmology. This is what our simulations show. This is what all our observations before Webb seem to confirm. True galactic maturity was supposed to take even longer. A mature galaxy has certain characteristics. It has a supermassive black hole at its center, millions or billions of times the mass of the Sun. How that black hole formed and grew so large is itself a puzzle, but the process requires time. Matter has to spiral inward. The black hole has to accrete mass gradually over millions of years. A mature galaxy has a diverse stellar population, old red stars that have been burning for billions of years. Young blue stars just recently formed. The chemical signature of multiple stellar generations, each enriching the cosmos with heavier elements. You can read a galaxy's history in the light from its stars. A mature galaxy often has structure, a rotating disk, spiral arms where star formation concentrates, a central bulge of older stars. These features develop through gravitational interactions, through the settling of gas into rotational patterns, through the slow dance of orbital mechanics operating over cosmic timescales. All of this requires billions of years, not hundreds of millions. The Milky Way, our home galaxy, has been assembling for most of the universe's history. It's still absorbing smaller galaxies even now. The Andromeda Galaxy, our nearest large neighbor, shows the scars of ancient mergers in the streams of stars that surround it. This gradual assembly is what makes sense physically. Gravity is patient. Star formation is self-regulating. When too many massive stars form at once, their combined radiation and supernovae blow away the gas needed to make more stars. The process has to pause, cool down, wait for new material to accumulate. The early universe in this picture should look messy. We expected to see small proto-galaxies, irregular blobs of stars, intense star formation happening in compact regions, the cosmic equivalent of construction sites. Structures still under assembly, foundations being laid for the grand galaxies that would emerge billions of years later. Every telescope before Webb supported this view. Hubble looked deep and saw smaller, more irregular galaxies at high redshift. The pattern seemed clear. The further back in time you looked, the less organized the universe became. This was the cosmic dawn as we understood it. This was the story we told. And then we pointed the James Webb Space Telescope at those same ancient regions of space and saw something entirely different. The James Webb Space Telescope sees in infrared light. This matters more than you might think. When light travels across billions of years of expanding space, it stretches. Visible light from distant galaxies shifts toward the red end of the spectrum and beyond, into the infrared wavelengths that our eyes can't detect. Hubble could see some infrared, but Webb was built specifically for this purpose. Its mirror is more than 6 times larger in area. Its instruments are cooled to just a few degrees above absolute zero, making them extraordinarily sensitive to faint heat signatures from across the cosmos. This means Webb can see further back in time than any telescope before it. When astronomers talk about redshift, they're describing how much the universe has expanded since light was emitted. A redshift of 1 means the universe has doubled in size. A redshift of 10 means it has expanded by a factor of 11. The higher the redshift, the earlier in cosmic history we're looking. Hubble could reliably see galaxies out to a redshift of about 8 or 9. Occasionally, it caught glimpses of candidates at redshift 10 or 11, but these were at the very edge of its capabilities, faint smudges requiring long exposures and careful analysis. Webb was designed to push far beyond this limit, to see the very first galaxies forming in the cosmic dawn. And it succeeded. Within months of beginning science operations, Webb identified galaxy candidates at redshift 13, redshift 15, some potential candidates even higher. These are galaxies whose light was emitted when the universe was only 200 to 400 million years old. We were seeing deeper into cosmic history than ever before. But it wasn't just the distances that surprised astronomers. It was what these galaxies looked like. Consider a galaxy designated Glass Z13. The name comes from the survey that found it. The Z indicates redshift. 13 is the estimated redshift value. If confirmed, this galaxy's light began its journey when the universe was about 330 million years old. But here's what troubles cosmologists. This galaxy appears to contain roughly 1 billion solar masses worth of stars. That's 1 billion times the mass of our Sun, all bound together in a single structure in an infant universe. Our models predicted that galaxies at this epoch should contain perhaps 10 million to 100 million solar masses at most. Glass Z13 appears to be 10 to 100 times more massive than it has any right to be. Or consider CEER S93316, another early galaxy candidate, possibly at redshift 16 or higher. If the distance estimates are correct, we're seeing this galaxy as it was just 250 million years after the Big Bang. Yet spectroscopic analysis suggests it contains stars that are already hundreds of millions of years old. Stars that formed even earlier than the light we're receiving. The timeline compresses to the point of impossibility. These aren't isolated cases. Survey after survey has revealed the same pattern. The early universe is filled with galaxies that appear too massive, too mature, too organized for their age. In some deep fields, astronomers have identified dozens of massive galaxy candidates in the first 500 million years of cosmic history. Not rare flukes, not one-off anomalies, a population. The masses are the most obvious problem, but they're not the only one. Many of these early galaxies show evidence of structure, disk-like shapes, elongated forms suggesting rotation. Some show hints of spiral patterns, though the resolution isn't quite high enough to be certain. These are features that should take billions of years to develop. Gravity needs time to smooth out irregularities. Gas needs time to settle into stable, rotating configurations. Then there's the stellar population issue. When you analyze the light from a galaxy, you can estimate the ages of its stars. Young, hot, blue stars emit different wavelengths than old, cool, red stars. Many of Webb's early galaxy candidates show evidence of both. They have young stars actively forming, which makes sense, but they also appear to have older stellar populations. Stars that would have had to form even earlier in the universe's history, during epochs where star formation should have barely begun. The chemical signatures tell a similar story. Spectroscopic observations of some early galaxies reveal the presence of heavier elements, Carbon, oxygen, nitrogen. These elements are manufactured inside stars and released when those stars explode. Their presence indicates that multiple generations of stars have already lived and died. The galaxy has been chemically enriched, but this process should require hundreds of millions of years at minimum, time that didn't exist. And then there are the black holes. Several early galaxies show the telltale signs of active galactic nuclei. That's astronomer speak for supermassive black holes, actively feeding on surrounding matter. The infalling material heats up and radiates enormous amounts of energy. We can see this signature even across cosmic time. The problem is that these black holes are already massive, millions of solar masses. Growing a black hole to this size requires time. It requires a steady supply of matter spiraling inward. The mechanisms we understand suggest timescales of hundreds of millions to billions of years. Some of the black holes Webb has detected appear to have formed within the first few 100 million years of the universe. That's not just surprising, it's difficult to explain with conventional physics. The abundance multiplies the mystery. If Webb had found one massive early galaxy, astronomers could invoke special circumstances. A rare fluctuation in density, a statistically unlikely but not impossible event. But Webb is finding these galaxies everywhere it looks. The early universe appears to be teeming with massive, mature structures. Statistical analysis of the galaxy counts reveals the scope of the problem. At redshift 10 and beyond, we're seeing far more massive galaxies than models predict. Not by a small margin, by factors of 10 or more in some mass ranges. The entire distribution appears shifted. It's not that massive galaxies are slightly more common than expected. It's that the whole population seems different from what our theories suggest should be there. Multiple independent research groups have analyzed the data, different teams using different methods. They arrive at the same conclusion. These observations are robust. The galaxies are real. The redshifts are reliable. The masses, while uncertain in exact value, are definitely much higher than orthodox models predict. Something about the early universe permitted galaxy formation to proceed much faster, much more efficiently than we thought possible. Either that, or our entire framework for understanding how galaxies assemble needs fundamental revision. These weren't measurement errors or cosmic flukes. The data was too consistent, too abundant. Something fundamental about our cosmic timeline was wrong, and astronomers began proposing radical solutions. The standard model of cosmology is called lambda CDM. Lambda represents dark energy, the mysterious force accelerating the universe's expansion. CDM stands for cold, dark matter, the invisible substance that provides the gravitational scaffolding for structure formation. This model has been remarkably successful. It explains the cosmic microwave background radiation in exquisite detail. It predicts the large-scale distribution of galaxies we observe today. It accounts for the abundance of light elements created in the first minutes after the Big Bang. For decades, lambda CDM has been the foundation upon which we've built our understanding of cosmic history. Its predictions have been tested and confirmed by countless observations. When the model said there should be acoustic oscillations frozen into the pattern of the cosmic microwave background, we found them. When it predicted how galaxy clusters should be distributed across space, observations matched. The model worked. But lambda CDM makes specific predictions about the early universe, about how fast structure should form, about how efficiently gas should cool and collapse into stars, about how long it should take for small, dark matter halos to merge into larger ones. And these predictions don't match what Webb is seeing. According to lambda CDM, the first galaxies should be small. Mass grows hierarchically through mergers. You start with dwarf galaxies containing millions of solar masses and build upward over billions of years. By the time the universe is 400 million years old, the model predicts typical galaxy masses should be in the range of 10 million to perhaps 100 million solar masses. Not billions, certainly not tens of billions. The star formation efficiency should also be limited. When gas collapses and forms stars, those stars emit radiation and eventually explode as supernovae. This energy blows gas out of small galaxies, preventing further star formation. It's a self-regulating process. The model accounts for this feedback and predicts that early galaxies should convert only a small fraction of their available gas into stars. Maybe 10%, maybe 20% at most. But some of Webb's observations suggest star formation efficiencies approaching 50% or higher, as if the normal feedback mechanisms weren't operating, as if something allowed gas to convert into stars with unprecedented speed and efficiency. When faced with observations that contradict predictions, scientists first check their measurements. Perhaps the redshifts are wrong. Perhaps we've miscalculated how far away these galaxies are. This was the initial hope. If the galaxies were closer than estimated, they would be younger in cosmic terms. More time would have been available for them to grow massive. Teams went back through the data. They checked photometric redshift estimates against spectroscopic confirmations. They looked for alternative explanations for the colors they were seeing. Could dust redden the light and make closer galaxies appear more distant? Could some unusual stellar population mimic the signature of extreme distance? In some cases, follow-up observations did revise initial estimates. A few of the highest redshift candidates turned out to be closer, less extreme. But the majority held up. Independent measurements confirmed the distances. These galaxies were genuinely ancient, genuinely early in cosmic history. Another possibility was that we're misinterpreting the stellar populations. When you look at a galaxy's light, you're seeing the combined emission from billions of stars. Teasing apart the ages and masses of those stars requires modeling. You have to make assumptions about what kinds of stars are present, how they're distributed, what elements they contain. Perhaps the models are wrong. Perhaps these early galaxies contain unusual stellar populations that make them appear more massive than they actually are. Maybe they're dominated by very massive stars that produce lots of light but don't actually contain as much mass as we're estimating. Astronomers explored this thoroughly. They tested different stellar population models. They varied the assumptions. In some cases, the estimated masses came down. But even with conservative assumptions, the galaxies remained too massive by factors of several times. The problem didn't go away. Dust became another candidate explanation. Dust absorbs blue light and re-emits it in the infrared. It can make galaxies appear redder than they actually are. Could dust be fooling us about the ages and distances of these galaxies? The difficulty is that the early universe shouldn't contain much dust. Dust is made of heavy elements produced in stars. The first few 100 million years of cosmic time shouldn't have seen enough stellar generations to create significant dust. And indeed, when astronomers looked carefully at the spectra, they didn't find evidence for the amounts of dust that would be needed to explain the observations. Each conventional explanation was examined. Each was found wanting. The observations were too consistent across different methods. Too many independent lines of evidence pointed to the same conclusion. These were genuinely massive, genuinely mature galaxies in a genuinely young universe. This left cosmologists in an uncomfortable position. The observations appeared solid. The standard model appeared inadequate. Something had to give. Some suggested that lambda CDM might need only minor adjustments. Perhaps the parameters we've measured aren't quite right. Perhaps the amount of dark matter is slightly different than we thought, or its properties are subtly different in ways that would enhance early structure formation. These would be tweaks rather than revolutionary changes. But as more data accumulated, it became clear that tweaks probably wouldn't be enough. The discrepancy was too large. The observations were too far outside the prediction envelope of the standard model. Either something dramatic happened in the early universe that our models don't include, or the fundamental physics governing structure formation works differently than we understand. This growing consensus didn't happen overnight. It emerged gradually through 2023 and into 2024 as more observations came in, as spectroscopic confirmations accumulated, as different teams analyzed the data independently and reached similar conclusions. The early universe was not behaving according to plan. The scientific community began to realize that solving this puzzle might require more than adjusting parameters. It might require new physics. As conventional explanations crumbled, physicists began considering more radical possibilities, ideas that would require us to rethink not just galaxy formation, but the nature of the early universe itself. When the conventional framework fails, physicists turn to speculation grounded in theory. They explore ideas that have been waiting in the wings, mathematical possibilities that seemed unnecessary when observations matched predictions. Webb's discoveries have brought these alternative models into the spotlight. One family of ideas involves modified gravity. General relativity describes how matter curves space-time and how that curvature produces what we experience as gravity. The theory has passed every test we've thrown at it for over a century. But perhaps, some theorists suggest, gravity behaved differently in the extreme conditions of the very early universe. Perhaps when matter density was extraordinarily high and space was compressed to unimaginable scales, subtle corrections to general relativity became important. If gravity was slightly stronger in the early universe, or if it operated over longer ranges than it does today, structure formation could proceed faster. Dark matter halos could collapse more quickly. Gas could fall into those halos with greater efficiency. The timescale for assembling galaxies would compress, potentially explaining why we see mature structures so early. The challenge is making such modifications work without breaking everything else. Any change to gravity affects the entire history of the cosmos. It would alter the formation of the cosmic microwave background. It would change the expansion rate of the universe. The model has to match not just Webb's observations, but all the other data we've gathered. Threading that needle is difficult, but several groups are exploring variations that might work. Another possibility involves primordial black holes. Standard cosmology assumes that all black holes formed from collapsed stars or through mergers in galactic centers. But what if some black holes existed before the first stars? What if tiny fluctuations in density during the first moments after the Big Bang created black holes directly? These primordial black holes could serve as seeds for galaxy formation. They would provide gravitational anchors around which matter could collect much earlier than expected. A black hole, already present in the first million years of cosmic time, could begin accreting matter immediately. It could grow rapidly. And the gravity well it creates could pull in surrounding gas, triggering intense star formation in its vicinity. If primordial black holes were abundant enough, distributed throughout the early universe, they might explain both the massive galaxies and the supermassive black holes Webb has detected. The timeline problem eases considerably if you don't have to grow black holes from stellar remnants, if they're already there, massive and hungry from the beginning. Dark energy, the force driving the universe's accelerated expansion, might also hold clues. We observe dark energy's effects today, but we don't know if its strength has been constant throughout cosmic history. Some theoretical models suggest that dark energy could have been different in the past. Perhaps it was stronger in the early universe, or perhaps it was weaker, or perhaps it didn't exist at all until later epochs. Changes in dark energy would affect how quickly structure forms. They would influence the battle between gravitational collapse and cosmic expansion. A period of enhanced structure formation in the early universe, driven by temporarily different dark energy conditions, might explain why galaxies assembled so efficiently. Then there are ideas about dark matter itself. We know dark matter exists because we see its gravitational effects, but we don't know what it's made of. We don't know its detailed properties beyond the fact that it clumps under gravity and doesn't interact much with normal matter or light. Most models assume cold, dark matter, particles moving slowly enough to clump on small scales. But what if dark matter had a brief period of different behavior in the early universe? What if it was initially warmer, suppressing structure formation, and then underwent some transition that made it cold and allowed rapid collapse? Or what if dark matter particles could occasionally interact with each other in ways we haven't considered, enhancing the growth of dense regions? Some theorists are exploring supercooled dark matter scenarios. In these models, dark matter undergoes a phase transition in the early universe, similar to water freezing into ice. This transition could release energy, stir up the matter distribution, and create conditions favorable for rapid galaxy formation. Inflation, the brief period of exponential expansion in the first fraction of a second after the Big Bang, might also play a role. Standard inflation theory predicts a nearly uniform distribution of matter after inflation ends. Small quantum fluctuations during inflation create the seeds of structure, but these seeds are supposed to be almost the same strength everywhere. What if inflation was more complex than we've assumed? What if different regions of space inflated for slightly different durations, or experienced subtly different physics during inflation? This could create larger initial density contrasts in some regions, patches of space where structure formation had a head start. If we happen to be observing such a region with Webb, we might see anomalously early galaxy formation without needing to change the physics of structure formation itself. Another intriguing possibility is direct collapse. Normally, stars form first and galaxies build up from there. But under certain conditions, a massive cloud of gas might collapse directly into a galaxy-sized structure without fragmenting into individual stars first. If the gas is too hot, or if it's rotating too slowly, the normal process of fragmentation might not work. Instead, the entire cloud could collapse together, forming a massive object all at once. This direct collapse might even create intermediate mass black holes directly, bypassing the need for stellar evolution entirely. A collapsing gas cloud of 10,000 or 100,000 solar masses could form a black hole of similar mass almost immediately. That black hole could then grow through accretion, seeding the formation of a galaxy around it. Some researchers are revisiting assumptions about the first generation of stars, population 3 stars, made purely of hydrogen and helium, are theoretical constructs. We've never observed one. Our models suggest they were very massive and short-lived, but these models rest on assumptions. What if the first stars were actually more diverse than we think? What if some were smaller and longer-lived, allowing them to persist and contribute to early galaxy building in ways we haven't considered? There's also the possibility that we're simply observing a rare region of space. Cosmic variance, astronomers call it. The universe isn't perfectly uniform. Some regions have higher density than average. Some have lower. If Webb happens to be pointed at an unusually dense patch of the early universe, we might see galaxy formation proceeding faster there than it does in typical regions. Each of these ideas is being actively developed by research groups around the world. Papers are published weekly proposing new mechanisms, testing new models against the data. The field is alive with theoretical creativity. No single explanation has emerged as the clear answer. Perhaps several of these mechanisms operate together. Perhaps the truth involves combinations we haven't yet imagined. What's clear is that the observations demand explanation. And as theorists generate possibilities, observers continue gathering data, refining measurements, and with each passing month, the picture of the early universe grows stranger and more detailed. Webb's observations didn't stop with those first dramatic images in 2022. The telescope continues to stare into the cosmic past, accumulating data month after month. And rather than clarifying the picture or revealing the early massive galaxies to be flukes, the observations have deepened the mystery. In the months following Webb's first release, astronomers focused on spectroscopy, where photometry estimates distance by measuring brightness in different filters. Spectroscopy splits light into its component wavelengths. It provides a direct measurement of redshift by identifying specific spectral lines and seeing how much they've shifted. It's more time-consuming than photometry, but far more reliable. The spectroscopic campaigns confirmed what the photometric surveys suggested. Many of the massive early galaxy candidates were exactly as distant as initially estimated. Their light truly did originate in the first few 100 million years of cosmic history. The redshifts were real, but spectroscopy revealed more than just distances. It provided chemical fingerprints. When you examine a galaxy's spectrum carefully, you can identify absorption and emission lines from specific elements: hydrogen, helium, oxygen, carbon, nitrogen. Each element produces a unique pattern of lines at characteristic wavelengths. In several early galaxies, Webb detected signs of oxygen and carbon. These elements don't exist primordially. They're forged in the cores of stars and released when those stars explode. Their presence in galaxies only a few 100 million years old indicates that stellar recycling was already underway. Stars had formed, lived their brief lives, and died, enriching their surroundings with heavy elements. All of this in a cosmic eye blink. The oxygen to hydrogen ratios in some of these galaxies approach levels we see in more mature systems. Not as high as in galaxies today, but far higher than expected for such young structures. This suggests surprisingly efficient enrichment. Either stars were forming and dying very rapidly, or the first stellar generations were particularly effective at producing and dispersing heavy elements. Then came the black hole discoveries. Active galactic nuclei, the brilliant cores powered by supermassive black holes actively feeding on matter, began appearing in Webb's data at redshifts beyond 10. These weren't subtle hints. These were unmistakable signatures. Broad emission lines indicating gas swirling around at tremendous velocities. X-ray emission detected by other space telescopes in the same regions. The characteristic spectra of matter being torn apart and superheated as it falls into a gravitational abyss. One such black hole residing in a galaxy at redshift 10.3 appears to have a mass of several million solar masses. The universe at that epoch was roughly 450 million years old. Growing a black hole to millions of solar masses in that time frame requires either continuous feeding at maximum possible rates or a massive seed to start with, or both. Standard models struggle to produce either scenario. Another active nucleus at even higher redshift suggests a black hole approaching 10 million solar masses. If the measurements hold, this represents a black hole that somehow assembled to enormous size in perhaps 300 million years. The accretion physics we understand places limits on how fast black holes can grow. They can't swallow matter faster than a certain rate without the radiation pressure from the infalling material blowing away additional fuel. These early supermassive black holes appear to be skirting or exceeding those limits. The mass distribution of early galaxies has also come into sharper focus. With larger samples and better measurements, astronomers have constructed what's called the stellar mass function. This describes how many galaxies exist at different mass ranges at a given cosmic epoch. It's a fundamental diagnostic of galaxy formation theories. At redshifts around 8 to 10, the stellar mass function observed by Webb sits well above theoretical predictions. There are simply too many massive galaxies. Not just at the highest masses, where you might invoke rare statistical fluctuations, but across the entire upper end of the mass distribution. The whole population appears shifted upward. Some analyses suggest the discrepancy is a factor of 3 to 5. Models predict a certain number of galaxies with masses above 1 billion solar masses at these epochs. Webb sees 3 to 5 times that number. Other analyses using different methods and assumptions find even larger discrepancies. Factors of 10 in some mass bins. This isn't a subtle effect requiring careful statistical analysis to detect. This is an obvious, glaring difference between prediction and observation. The early universe was far more efficient at building massive galaxies than our models allow. Star formation rates add another layer to the puzzle. By examining the ultraviolet light from early galaxies, astronomers can estimate how rapidly they're converting gas into stars. The rates are astonishingly high. Some early galaxies appear to be forming stars at rates of hundreds of solar masses per year. That's comparable to the most extreme starburst galaxies we see in the later universe, where major mergers or other dramatic events trigger intense bursts of star formation. But these early galaxies don't have the luxury of major mergers. There aren't many other galaxies around to collide with. They're forming stars at extreme rates through some internal process we don't fully understand. And they're maintaining these rates for extended periods, long enough to build up billions of solar masses of stars. The efficiency of converting gas into stars also appears remarkably high. When you account for the total mass in a galaxy's dark matter halo and estimate how much normal matter should be associated with that halo, you can calculate what fraction has turned into stars. In nearby galaxies, this fraction is typically 10 to 20%. In Webb's early galaxies, some estimates suggest 40 to 50% or more. It's as if the normal regulatory mechanisms that prevent gas from turning entirely into stars weren't operating effectively. Supernova feedback should blow gas out of galaxies. Radiation pressure from massive stars should heat and disperse surrounding clouds. Something should limit star formation efficiency. But in the early universe, these limits seem weaker than expected. Morphological studies have revealed structure in early galaxies that shouldn't exist yet. Elongated disks, hints of spiral patterns, though resolution limits make these difficult to confirm definitively. Some early galaxies show evidence of central bulges, dense concentrations of stars in their cores. These are features that develop through dynamical processes operating over long timescales. Gravitational interactions, orbital resonances, the slow settling of matter into equilibrium configurations. Seeing such features at redshift 10 or 12 suggests that dynamical evolution proceeded much faster than anticipated. Either that, or these galaxies are older than their redshift suggests, which brings us back to the fundamental timeline problem. Multiple independent surveys using different parts of the sky, different instruments on Webb, different analysis techniques have all found consistent results. The pattern holds across the board. The early universe doesn't look like we expected it to look. These observations are forcing us to confront a humbling reality. The universe's first billion years remain far more mysterious than we imagined, and our cosmic origin story needs revision. Before we lose ourselves in uncertainty, it's worth clarifying what remains solid. The Big Bang itself is not in question. The evidence for a hot, dense beginning to our universe is overwhelming. The cosmic microwave background radiation fills the sky with precisely the spectrum predicted by Big Bang cosmology. The abundances of light elements, hydrogen and helium and lithium, match calculations of primordial nucleosynthesis with remarkable accuracy. The expansion of the universe, first discovered nearly a century ago, continues to be measured and confirmed by countless observations. The age of the universe also remains secure. Multiple independent methods converge on 13.8 billion years. We measure the oldest stars and find none older than this. We calculate the expansion history from supernova observations and cosmic microwave background data and arrive at the same age. We model stellar evolution and galaxy formation, and everything fits within this timeframe. Webb's observations don't challenge the cosmic clock itself. What's being reconsidered is the detailed timeline of structure formation. How quickly did the first stars ignite? How rapidly did galaxies assemble? How efficient were the processes that converted primordial gas into organized stellar systems? These are questions of astrophysical mechanisms, not cosmological fundamentals. The Lambda-CDM framework, with its dark matter and dark energy, also remains largely intact. Dark matter is still necessary to explain how galaxies rotate, how clusters hold together, how gravitational lensing bends light. Dark energy is still required to account for the accelerating expansion we observe. The basic architecture of the model survives, but within that architecture, something is missing. Some process or phenomenon that operates in the early universe, but that our current models don't capture. This is what cosmologists are searching for now. One possibility is that the initial conditions were different than we've assumed. When inflation ended and the universe transitioned into the hot Big Bang phase, perhaps the distribution of matter wasn't quite as uniform as our simplest models suggest. Perhaps there were larger density fluctuations in certain regions. Perhaps the statistical properties of these fluctuations differed from what we've been using in our simulations. If the early universe had a few more high-density peaks than expected, those peaks could collapse earlier and form structures faster. This wouldn't require changing the physics of gravity or star formation. It would just mean that the starting conditions were more favorable for rapid structure formation than we thought. The challenge is reconciling this with cosmic microwave background observations. The microwave background shows us the distribution of matter when the universe was 380,000 years old. It looks very uniform, with density variations of only about 1 part in 100,000. Large initial fluctuations should leave imprints in this radiation. So far, we don't see anything obvious. But perhaps there are subtle features we've missed. Or perhaps the fluctuations were on scales smaller than the microwave background can easily probe. Feedback mechanisms might also be different than we model. When massive stars explode as supernovae, they inject enormous amounts of energy into their surroundings. This energy heats gas and can blow it out of galaxies entirely, shutting down future star formation. Our simulations include these feedback effects, but they're based on extrapolations from what we observe in the nearby universe. Perhaps in the early universe, with different densities and different metallicities, feedback operated differently. Perhaps gas could cool and collapse faster than supernova explosions could disperse it. Perhaps the geometry of early galaxies, their shapes and density profiles, made them more resistant to feedback than later systems. Small changes in how feedback operates could lead to significantly different star formation efficiencies. The formation and growth of black holes may also involve physics we haven't fully grasped. We know that supermassive black holes exist in most large galaxies today. We know they must have grown from something. But the detailed pathway from stellar mass black holes to million and billion solar mass monsters remains uncertain. If there are ways to form massive seed black holes early on, perhaps through direct collapse of gas clouds or through dense stellar clusters, the timeline for black hole growth becomes less problematic. These seeds could begin accreting immediately, growing rapidly in the gas-rich environment of the early universe. Their growth might even trigger galaxy formation around them, inverting the usual picture where galaxies form first and black holes grow within them. There's also the question of cosmic variance. The universe is vast and different regions have different densities. We observe only a tiny fraction of the total volume. If galaxy formation is a stochastic process with significant random variation, we might simply be looking at regions where things proceeded unusually fast. Statistical fluctuations are a real phenomenon in cosmology. The density field is random on small scales. Some regions get lucky and collapse early. Others lag behind. If Webb happens to be observing particularly overdense patches of the early universe, we'd naturally see more and earlier galaxies there than in typical regions. The difficulty with this explanation is quantitative. The number of massive early galaxies Webb sees seems too high to explain through ordinary statistical fluctuations. You'd need to be observing very rare regions indeed. And Webb is looking at multiple fields in different directions on the sky. They can't all be exceptionally rare overdensities. Another aspect under scrutiny is star formation itself. We model how gas clouds collapse and fragment into stars based on physics we understand and observations we've made. But star formation in the first galaxies, in gas with no heavy elements, might differ from star formation today. Without metals to help cool the gas, cloud fragmentation might be suppressed, leading to more massive individual stars. But more massive stars burn brighter and die faster, potentially speeding up the entire cycle of stellar birth and death. They also produce more energetic supernovae, which could either suppress or trigger further star formation depending on the details. The initial mass function, the distribution of stellar masses that form in a given star-forming episode, might also be different in the early universe. If the first stars tended toward higher masses, they'd produce more light per unit mass, potentially making early galaxies appear more massive than they actually are. Though this effect can only account for part of the discrepancy, not all of it. What emerges from these considerations is a picture of genuine uncertainty. Not uncertainty born of poor data or sloppy analysis, but the productive uncertainty that drives scientific progress. We have solid observations that don't fit our models. We have multiple possible explanations, each with strengths and weaknesses. We're in that uncomfortable but exciting phase where the old framework has cracked, but the new one hasn't yet crystallized. This is how science advances, not through steady accumulation of confirming evidence, but through moments of tension when observations force us to question our assumptions. Webb has given us such a moment. The early universe is telling us something we didn't expect. Now we have to listen carefully and figure out what it means. As we stand at this crossroads in cosmology, it's worth stepping back to appreciate what this moment means, not just for science, but for our place in the cosmic story. Humans have always looked up and wondered about origins. Every culture across every continent has developed stories to explain where everything came from: the cosmic egg, the primordial waters, the void that preceded creation. These stories served a fundamental need, the need to understand our place in the larger pattern of existence. What makes this moment in history remarkable is that we're rewriting our origin story based on direct observation. We're not speculating or imagining. We're actually looking back in time, gathering photons that have traveled across most of the universe's history and reading in those photons the story of how structure emerged from simplicity. And now that story is changing, not in its broad outlines, but in its crucial details. The timeline we thought we understood, the careful sequence of events from the Big Bang to the first stars to the first galaxies, is being revised in real time. We're living through a moment of genuine discovery when the universe reveals itself to be stranger and more wonderful than we imagined. This requires a certain humility. We've been wrong before. In the 1920s, we didn't know the universe was expanding. In the 1930s, we didn't know about dark matter. In the 1990s, we didn't know the expansion was accelerating. Each generation of astronomers has been confident in their understanding, and each has been surprised by what new instruments revealed. The James Webb Space Telescope is delivering that surprise to our generation. It's showing us that galaxy formation in the early universe proceeded faster and more efficiently than we predicted. It's challenging our models. It's forcing us to reconsider mechanisms we thought we understood. But this isn't a failure. It's an opportunity. Science doesn't progress through eternal confirmation of existing ideas. It progresses through productive tension between theory and observation. When the two disagree, we learn something new. We refine our understanding. We discover aspects of nature we hadn't previously considered. The scientific method is fundamentally a system for being wrong in increasingly precise ways. We build models. We test them. When they fail, we build better models. The process is iterative, self-correcting. It doesn't claim absolute truth, only progressive approximation of reality. What Webb has shown us is that our approximation of early galaxy formation needs improvement. We don't yet know exactly how to improve it. Multiple research groups are exploring different possibilities. Some will lead nowhere. Some might lead to incremental advances. One might eventually lead to a breakthrough that reshapes our understanding. This work is ongoing, not settled. The next few years will bring more observations, deeper surveys, better spectroscopy. Statistical samples large enough to distinguish between competing models. The uncertainties will gradually narrow. The picture will sharpen. There's an existential dimension to all of this that's worth acknowledging. These early galaxies we're observing, these impossibly mature structures in the infant universe, are part of our ancestry. The heavy elements they created through stellar fusion eventually found their way into later generations of galaxies, into planetary systems, into the molecules that make up everything we've ever known. The iron in your blood was forged in a star. The calcium in your bones was created in a supernova. The oxygen you're breathing right now was produced by stellar fusion billions of years ago. We are, in a very literal sense, made of stardust, made of the processed remnants of ancient stars that lived and died long before our sun ignited. Some of those stars may have existed in the very galaxies Webb is now observing. Stars that formed when the universe was only a few 100 million years old. Their light has long since faded. Their remnants have been scattered and recycled many times over. But they were part of the chain of cosmic evolution that eventually led to us. Understanding how those first galaxies formed isn't just an academic exercise. It's understanding our own deep history. The conditions that allowed rapid galaxy formation in the early universe created the cosmic environment that would eventually give rise to planets and life. If galaxies had formed more slowly, the universe's chemical enrichment would have proceeded differently. The abundance of heavy elements would be lower. The timeline for planet formation would shift. We don't yet know whether life requires a specific cosmic timeline. We don't know if the rapid galaxy formation Webb has observed makes life more or less likely in the early universe. These are questions for future research, but they're profound questions. Questions about habitability and possibility and the distribution of life across cosmic time. Looking ahead, several missions will continue this investigation. Webb itself has years of observations ahead. Its instruments will keep peering into the cosmic past, accumulating spectra, measuring masses, mapping the early universe in ever greater detail. Ground-based telescopes are also contributing. The largest optical telescopes on Earth, equipped with adaptive optics that correct for atmospheric blurring, can provide complementary observations. They can survey larger areas of sky, identifying candidates for Webb's detailed follow-up. Future space telescopes are already being designed, missions that will push even deeper into the cosmic dawn. Instruments that will measure the faint signatures of the very first stars, the population 3 giants that have never been directly observed. Projects that will map the large-scale structure of the early universe and reveal whether the massive galaxies Webb found are typical or exceptional. There's something beautiful about not having all the answers yet, about standing at the edge of knowledge and seeing questions stretching out ahead. It reminds us that the universe still holds mysteries, that observation can still surprise us, that nature is more creative than our theories. The galaxies are there in the data, ancient and impossible. Real structures that form through real physical processes we're still working to understand. They're not going away. They're waiting patiently for us to figure them out. And we will. Not immediately. Not through a single breakthrough. But gradually, through the careful accumulation of observations and the patient work of theory, we'll understand how the early universe assembled galaxies so quickly. We'll revise our models. We'll write a new chapter in the story of cosmic evolution. That story is our story. It's the account of how matter organized itself into increasingly complex structures, how atoms became stars, how stars became galaxies, how galaxies became the cosmic web, how, in at least one corner of one galaxy, matter became aware of itself and began asking where it came from. We're part of an ongoing conversation between humanity and the cosmos. We ask questions through our telescopes. The universe answers through its light. And sometimes, as with Webb's observations of early galaxies, the answers surprise us. They challenge us. They invite us deeper into the mystery of existence.